Hi, welcome. My name is Corey Glodek, and I'll be reviewing a paper, Multi-UAV Navigation for Partially Observable Communication Coverage by Graph Reinforcement Learning. The author's purpose of this was to design a model to maximize target coverage using UAVs. The approach that they wanted to take was a deep reinforcement learning model with a centralized training environment and a decentralized action environment. The applications for this would be, think, post-disaster scenario, like after a hurricane that knocks out communications for a wide swath of the region. You know, clearly they're going to use, they used a multi-agent deep reinforcement learning model. As I said before, each UAV has its own model, and that's what it uses to take its actions or devise the probability for what the best next action is. Centralized training, it goes to a main hub, and then it passes back the updated model to each individual agent. Here's a high-level architecture of the model and the network that they used. So each UAV, each agent takes its observations, passes it through an encoder, checks its adjacency graph, sees they only went for one hop away. So one hop, whatever's right adjacent to them, grabs their observations to concatenates everything. And then it goes through the actual model training. So they used a GRU with a linear transformation. This is just a DQN, but with a GRU. The overall model that they preferred to go with, they made two models. One was the Dragon, and this is the S-Dragon. But ultimately, it's just a DQN. It's using soft learning, so it's going more based off probabilistic estimates for its actions, and then uses that. Here's the probability. They used a softmax here. I think for the regular Dragon, they used a linear, so it was either or. Now note, they're kind of using non-standard notation, and we'll get more to that later. So, similar to like a double DQN, which most DQNs do have the target and the learning model. That's how they went through and approached it. The whole premise of having the learning and the target is for stability of the model. And the target will be updated from time to time based on what the learning is. So here's the updating of the central model. Here's your Q loss, here's your reward function. It's a summation of all of this. The reward, the value, and then the current action, best action from the Q table. And this is, to some of you, this might look familiar. This is a Bellman equation, and that's what they're trying to minimize. Now, we're talking temporal difference. They're looking one step ahead. And you can see that in the value function here. Alpha is your learning, and then they're taking the log summation of what that next step is. And that's Q prime is the next probable action. Using the target network for the next step. Here's the evaluation criteria and reward function. The reward for the agent itself, pretty straightforward, number of points it's covering. It's one hop adjacency. Again, it's kind of the average. It's, how many are in one hop. And then also, since these are not permanently powered, they're running on a battery. So energy plays into it. If the agents go off the map, they take a negative function or negative reward that's added to it. Otherwise, it's just all of these. And here's the whole wrap up. Now, this is for the reward function. Now, the evaluation criteria that they're going to look at during the training and the testing is more this. Coverage index, fairness index, which kind of like normalizes some of it, energy index, and then they roll it all up. Fairly straightforward. You don't need anything overly crazy here. So during the training and testing, they tested a number of different models. Here are the reinforcement learning models. They did do some non-RL models, but they did not test very well at all. The overall environment, 200 square. They have 120 targets that are in their training phase. They only used 20 UAVs. During testing, they varied it just to see if density changed it. So each episode was about 100 time steps. They did 160K episodes each. Yeah, you can do the math. That is a lot of episodes. A lot of time steps too. And then they did the comparison against those models. Here are the overall results. Overall, pretty good on all of them. There's more stability on, on most of these than the regular DQN and the ComNet. Don't worry about that. It's just there's some stability issues with the ComNet. It's the way that the communication protocol works. So at about 30,000 training episodes, you start to see some convergence here in terms of the learning. Like all of them do, even the ComNet, if you take that spike away. But the two that they designed performed the best, and you can see that up at the top. And this is during the training. So for their test results, they ran each of these, the final models, using 20 UAVs for 100 episodes, and then plotted the results over here. Again, their two models performed the best. DGN worked also fairly well. And over here, you see your global metrics. This is the CFE score. So there's, they split it up, and you can see what the average is. And you can see that it increases, does it fairly well. And that's it. Questions, concerns, complaints? And here's your citation.